Yeah, I'd like to start by thanking the organizers for the opportunity to present here. So I'll be talking about a three-dimensional quantum spin liquid. It's called quantum spin ice. And there have been very interesting recent development on what we call dipolar-octupolar particle material. So since not everyone here is familiar with the quantum spin ice system, I'd like to give you some general introduction to the subject. So let me start with the classical spin ice. So we are talking about some Ising model on the particle lattice. And as you know, a particle lattice is a corner sharing tetrahedron. So when you write down an Ising model on this lattice, then what we can show that we can rewrite this model like this. So you first consider cluster spin. So you have a sum over Ising spin on each tetrahedron. Then you scale them. The sum of all tetrahedron. You are counting every side twice. So you multiply one half factor there to correct the mistake. Then this model is equivalent to this model of the constant. At the classical level, it's clear that in order to minimize the energy, I want that cluster spin to be 0 all the time. And that's the reason why you end up with so-called 2-in, 2-out spin configuration. And in fact, if you look at the just single tetrahedron, then we know that there are already 6 possible configurations. So imagine that you tie this entire lattice with this configuration, you end up with a massive degeneracy. So you have a exponentially large number of spin configurations that will give you exactly the same energy. So in order to make this thing quantum, you just add a transverse interaction so that now you allow fluctuation of the spin. So you have this XY type interaction here. Then in the limit that your transverse coupling is much smaller than the Ising coupling, you can do a degenerate polarization theory. Within that degenerate manifold, you end up with this 6-spin ring change interaction around this hexagonal loop on the particle lattice. So what this guy does is like this. So if you start with one of the 2-in, 2-out configuration in the manifold, and if you flip the spin around the hexagon, then you end up with some other configuration, and you will find that this configuration is different from this guy, but this belongs to that massive degenerate manifold. So by applying this ring change term over and over again, you can essentially generate this large number of degenerate spin configuration. So you can imagine that by doing so, the quantum grounds of this model could be some massive superposition of this degenerate spin configuration. That's the way that we arrive at a quantum spin liquid state. So one way to see this physics is through this mapping to quantum electrodynamics, and this is where all the interesting physics comes about. So you can map your G component to spin to an electric field, and the spin raising operator to e to the I vector potential. So then the usual commutation relation between Sz and S raising operator becomes a commutation relation between my vector potential and the electric field. So as you know, this is the usual canonical commutation relation. So if you think about electric fields as a coordinate, then my vector potential will be a canonical momentum. So if you do this, then the fact that cluster spin should be always 0, this can be mapped to this Gauss law problem. So basically cluster spin equals 0 constraint becomes a Gauss law. And more interestingly, the ring change term, if you just plug in this expression here, then the ring change term becomes a cosine curl of A defined around the hexagon. So then you realize that your effective Hamiltonian looks like this. So this term comes from the ring change term. And this electric field square minus 1/4 comes from the fact that we are dealing with the spin half object. So the magnitude of SG has to be basically plus minus 1/2. So we constrain that the electric field square has to be 1/4. So then you end up with this lattice U1 quantum electrodynamic Hamiltonian. on the particle lattice. So now you can map this problem to a lattice quantum electrodynamics problem. And now, if you are in so-called in the deconfined phase of this quantum electrodynamics Hamiltonian, then you can expand this cosine term to, say, quadratic order. Then you end up with this Hamiltonian. Basically, you get E squared plus B squared Hamiltonian. Then that's the usual electrodynamics Hamiltonian. And so by doing so, we would expect that there are three kinds of emergent excitations in this problem. So the most obvious one is the spin-on excitation, or what we call electric monopole. So you just flip the spin, one of the spin, then the energy cost for that will be J sub z, basically the Ising interaction cost. If you do so, then you generate what we call a spin-on anti-spin-on pair excitation. So what actually happens is that you end up with 3 out, 1 in, and 3 in, 1 out configuration. This one we call spin-on anti-spin-on excitation. And then there's an emergent photon because of this electromagnetic Hamiltonian. So you get a linearly dispersing mode with a T cube heat capacity. And there's also something called the magnetic monopole, or some people call Vizon, and that has the energy scale of ring exchange interaction. So you would expect that you should see all of this emergent excitation in the problem. So far, the best candidate material for this physics is this 227 particle material. In particular, the cerium 3+ ion is a magnetic ion. So there are various cerium-based materials like this. So on the crystal electric field environment, is the 4F1 configuration with the J equal 5½ The lowest Kramer's doublet consists of mj plus minus 3½ and the excitation energy to the next level is 50 million volts. So it's very big. So it's like 580 Kelvin. So this is a very well-defined Kramer's doublet. And now it turns out that this lowest doublet can be described by this kind of pseudo-spin degree of freedom. So X component will be actually the octupolar operator. That tau y is also octupolar. And tau z is the dipolar operator. But it turns out that tau x and tau z, they actually transform like a dipolar operator under a lattice symmetry operation, even though this guy is, in principle, octupolar in character. So the most general Hamiltonian one can write down based on symmetry looks like this. So it's an actually XYZ time model. But because of the fact that tau x and tau z, both of them transform like a dipolar operator, you actually allow a mixing between two systems. And notice that because of the fact that these two objects are basically octupolar operator, the external magnetic field preferentially coupled to the dipolar degree of freedom. So essentially, you only couple to this dipolar degree of freedom, and that will be very important for the physics that I'm going to describe. And so you can simplify this model by making a simple transformation. Basically, you just get rid of this mixing term, then you end up with XYZ model. And the price you have to pay is that X and Z component is now a mixture of dipolar and octupolar operator. But they really transform like a dipolar operator. So in this language, you can think of X and Z as a dipolar operator and the tau y, sorry, SY as an octupolar operator. And because of this, now in this coordinate, your external field couples to both X and Z component, but it doesn't couple to Y because it's an octupolar degree of freedom. So with that, you can map this problem again to a quantum electrodynamics problem. So again, I'm going to use this language that if there's a dominant Ising degree of freedom, then I call that electric field, and the raging operator with e to the I vector potential. But remember that when you flip the spin, one of those spin, starting from 2 in 2 out configuration, you end up with this 3 out, 1 in, or 3 in 1 out configuration we call spin-on anti-spin-on. The spin flip essentially create spin-on and anti-spin-on pair, and that's why this raging operator contains both creation of spin-on and anti-spin-on excitation. So this representation really reflects this physics. So with this, you can map this problem to a quantum electrodynamics problem like this, as I described to you, and the sign of K depends on whether transverse coupling is ferromagnetic or anti-ferromagnetic. And for example, imagine that my octupolar exchange interaction is the dominant. If this is the largest coupling, then in this case, the Y component or octupolar operator should scale like electric field, and the spin raging operator will be a combination of X and Z component. And depending on the sign of K, you have two different kinds of ground state. Basically, if K is positive, then you want curl of A to be 0. If K is negative, you want curl of A to be negative. Sorry, curl of A to be pi. So that's why we call this case zero flux quantum spin ice. And this one will be a pi-flux quantum spin ice. So there are two different kinds of vacuum, if you like, or ground state for this model. So this is the case when octopolarizing is dominant. But if oh, it's not working. Okay. But on the other hand, if dipolarizing coupling is dominant, then again, X component will be electric field, and the other combination will be a spin and anti-spin excitation. Again, there are two kinds of possibilities, either zero flux or pi flux. There are four kinds of quantum spin ice that you can possibly get out of this kind of model. And we looked at the phase diagram. So this is the schematic phase diagram. So depending on whether octopolar is dominating or dipolar is dominating, the phase diagram is pretty similar, but nonetheless, there's a zero flux state or pi flux state. The pi flux state essentially dominates the phase diagram. And there have been very elaborate experiment basically using thermodynamic data such as heat capacity and spin susceptibility, especially Bruce Golan's group did an amazing job trying to find reasonable exchange parameters that determine this Hamiltonian. And it turns out that, for example, in Bruce Golan's group, showed that this material, cerium zirconate, may be very, very close to this phase boundary between a pi flux octopolar or a pi flux dipolar quantum spin ice state. So according to this phase diagram, but both possibilities could fit the thermodynamic data very well. So at this point, it's not clear which one may be a preferred scenario. There's some other analysis that suggests that this material may be here, but we don't really know the precise location of the system. I have to say there's no first principle determination of exchange coupling, and if somebody can do this, that would be fantastic. But we don't have this calculation yet. So we just based on this analysis here. So we used what we call a gauge mean field theory. It's just based on the representation I told you about. I just want to say, using this formulation, we can actually compute spin-spin correlation function, or the static and dynamical spin correlator that can be measured by neutron scaling experiment, and that's something that I will talk about here. So one thing I like to emphasize is that if you're talking about coupling to the neutron, and in terms of original degrees of freedom, the neutron will only couple to this dipolar degree of freedom. The G factor for this degree of freedom will be finite. So this will be a neutron scattering cross-section, but in the new pseudo-spin language, both X and Z couple to the neutron. And depending on which Ising coupling is dominant, there are two possibilities. So in this case, the X component will be related to the photon degree of freedom. Z component will be related to the spin-on degree of freedom. So you can observe both emergent photon and spin-on. But this case, you're only sensitive to spin-on excitation, and you cannot see a photon excitation. So depending on which case is realized, you may or may not see photon excitation, but you will always see spin-on excitation. So please keep in mind that. So, so the general expectation is that if you're here, you should see both photon excitation in the neutron scattering experiment as well as a spin-on. But if you're here, then you only see a spin-on excitation. So going back to the experiment, so this is the experimental data from Bruce Golan's group. It's the equal time structure factor, or the Fourier transform of equal time structure factor. And theoretically, we can compute this equal time structure factor for zero flux state and pi flux state. And here we are only taking into account the spin-on degrees of freedom. And you see that we can see that in the static structure factor in the scattering plane, this HL scattering plane, you can see the modulation of the intensity around this rod-like structure here, and that's very, very similar to the experimental result. On the other hand, the structure factor from the zero flux state is very, very different. So this already tells you that what Bruce sees here is very likely to be a pi-flux quantum spin I state, and that's consistent with Bruce's parameterization. And more interestingly, we can now compute dynamical spin structure factor. And what happens in the pi-flux state is that because of the pi-flux background, there's a doubling of the unit cell. So instead of the single spin-on band, I have two spin-on bands. And because of that, I have this very, kind of flat spectrum, and I have two bands of spin-on. And because of this, if you compute the dynamical spin structure factor, then remembering that dynamical spin structure factor always measures the pair excitation of spin-on and anti-spin-on, you end up with the three kind of very flat dynamical spin structure here, basically two interband and one interband transition. Okay. So then it turns out there is a very recent experiment done by Roman Sibyl, and they looked at the serum tin material, and they saw this inelastic spectrum that can be explained by a sum of three Gaussian, and you can fit this thing with our theory, and then you end up with this a reasonable fit with the pi-flux quantum spin I state. The exchange parameters you determine is pretty close to what was determined by thermodynamic data. And interestingly, the very, very recent polarized neutron scattering experiment done by Peng Dai's group at Rice showed that in addition to this three-peak structure that we predicted for the pi-flux state, they also saw quasi-elastic scattering that was not seen before in the other material. So at very low temperature, they also see this sort of emergent photon contribution. If this is true, then what that suggests is that perhaps the dominant eigencoupling is dipolar, not octupolar. If photon is absent, then it has to be the other way around. So I think, so you should be able to distinguish two different cases in principle, but this experiment, assuming that this is correct, then it should be a dipolar case. Okay. So on top of this, another amazing experiment was a heat capacity experiment, and this is the heat capacity data at very low temperature. They were able to measure this thing down to 20 millikelvin. This is the work done actually in Vienna, and it looks like the low temperature heat capacity could be fit to the exponent 3. So this is what you'd expect from the photon excitation. In fact, the photon velocity we get out of this is very similar, or the same order of magnitude as the photon velocity I will get from the neutron scattering experiment that I told you about. So this is these set of experiments are very encouraging, and perhaps it suggests that this material is really a good candidate for quantum spin I. So I think that's all I want to say. Thank you very much.